Welcome to my bathroom. What do I have here? Here I have 2 tubs of water. I also have a slice of bread and what's called a bath bomb, which is basically a little effervescent tablet that you can put in the bath, and it bubbles and fizzes and adds a lot of cool coloring to the bath and a little bit of soap. So, these bath bombs are sort of fun things that kids and grown-ups can use in the bath. Usually people don't use bread in the bath. But what I want to demonstrate today is the difference between surface and bulk erosion. So if I threw the bread in the water, well, we know that, once that bread takes on a lot of water, the bread is pretty porous and the water can diffuse pretty readily within the bread. And eventually this piece of bread is going to deteriorate, where basically it's all just going to become a whole bunch of crumbs. Some of the components of the bread are going to dissolve, and other components of the bread are just going to sort of fully break apart. And a bath bomb, on the other hand, basically dissolves or reacts very quickly with the water, and basically it erodes from the surface. So the bread is what I would consider a case of bulk erosion, where diffusion can happen very readily through the whole material, and basically no matter where you are in the material, it's degrading, whereas this reacts so quickly with the water around it, that only really the stuff at or very, very close to the surface dissolves, and the bulk remains intact. So, ready, set, woohoo! So you can see it's dissolving, a bunch of fizzing coming up. It's a good bit of fun. The bread, not really much happening here. So if you're to think about things in the context of the second Domkohler number, the reaction rate is so slow and the diffusivity is so high that this one definitely would experience bulk erosion. And in contrast here, the reaction rate is pretty quick, right? You can actually physically see the reaction happening. I think these bath bombs are sodium citrate and citric acid reacting with one another, and the bubbles coming off are CO2, I believe. And you can see, if I don't spill it, you can see that the bubbles are coming off, and only really coming off very close to the surface. And I mean, it's a little bit porous, but definitely not porous enough for that water to have penetrated all the way to the center. And if I pick it up, we can see that it still has its mechanical integrity intact. Only a little bit at the surface has really reacted, and if I were to cut it open and look at the center, the stuff at the center would have barely reacted at all. So, happy bath bombing, everyone. Or bath bedding. This one's the recommended one. Actually, I misspoke earlier when I said the ingredients were sodium citrate and citric acid. You see, it's sodium bicarbonate and citric acid. So, yeah, it's an acid-base reaction releasing the carbon dioxide from the sodium bicarbonate. Welcome to Biomaterials. What are we going to talk about today? Today we're going to talk about 2 mathematical models for predicting either how many bonds are remaining within a polymer as a function of time, or how much volume is remaining. And in particular, we're going to study those 2 relationships, one for what bulk degradation looks like and one for what surface degradation looks like. So we're basically going to study mathematical models to predict polymer degradation. And we're going to do so for the 2 modes of polymer degradation that I sort of showed at the live demo at the beginning of this class. So we're going to do so for bulk degradation, and for bulk degradation, if you remember from the previous lecture, the idea with bulk degradation is the volume remains approximately constant. For volume, I must use this sort of V with a weird cross through it to signify volume. So the volume is constant, and we want to predict within that volume how the concentration of bonds varies with time. And in particular, can we predict this bonds as a function of time, can we predict this as like some kind of mathematical function? Spoiler alert, yes. And we're going to do that today. We're going to derive that. The second mathematical treatment is for surface degradation. For surface degradation, the volume is something that varies with time. And that's the mathematical function that we want to predict. But within that volume, the concentration of bonds is constant. And it's essentially just the surface that's eroding as a function of time. So this was like the bath bomb. This is like the bread. But in the context of bioengineering, these could be drug delivery devices. These could be structural implants. These could be coatings for things. This is what we want to be able to predict. And so let's get started with this model for bulk degradation first. So for bulk degradation, but before we get into the model for bulk degradation, let's just remind ourselves of the chemistry. Let's sort of consider a polyester. And if we had a polyester, the reaction for degradation might look something like this. We have an ester bond plus an H2O, and this goes to degradation products. And although strictly speaking, this is a reversible reaction, the degradation products are something like a COOH and an OH group. And although strictly speaking, those could hypothetically recombine to form an ester bond and a water, oftentimes, for example, polylactic acid or polyglycolic acid, the degradation products are carbon compounds that our body metabolizes to something else. So basically, if your body's metabolizing and constantly pulling away those degradation products, they are unlikely to recombine to form an ester bond. So we sort of treat this as like a one-way street, as a reaction that doesn't go back the other way. So basically, this is happening here. And if we wanted to be strict with our chemistry, anytime you have two things that react with one another in an elementary reaction that forms a product, if we want to be strict with our kinetics, it would look something like this. The time rate of change of ester bonds, or the time rate of change of the concentration of ester bonds, is equal to minus some true rate constant times the concentration of ester bonds times the concentration of H2O, where essentially the concentration of each of the products is sort of a proportionality for the rate of degradation. And since these ester bonds are on the left-hand side going to degradation products, we have a minus sign here, and we have some K, some true K that's associated with this. In real life, in the body, this concentration of H2O, this H2O is always there, right? Like, the insides of our bodies are always wet, so this is basically approximately constant, right? There's it's not like you put some polyester inside someone's body and all of a sudden they get dried out. It's all of a sudden like all the water in you is depleted. Nope, there's plenty of water in us, and that water is always constant. So what people do is they typically combine this true K and the concentration of H2O. They basically combine them into an effective K. So what's the deal here? So in practice, people basically say, hey, it's D ester bonds, or deconcentration of ester bonds dt is equal to minus some K effective times the concentration of ester bonds. Where people have lumped together the concentration of H2O in this K. Whoops, sorry, I have my arrows in the wrong place. people have lumped together these two parameters into this single K effective right here. And this is that K effective that we were talking about in the previous lecture. So basically, the more ester bonds there are, the higher chance any one of them could break at any given time. There's some proportionality constant K effective, which is incorporated into here. Now, for the remainder of the lecture, I don't feel like writing concentration of ester bonds sort of in brackets right here, so I'm just going to call concentration of ester bonds. I'm just going to call this concentration of B. So that's what I'm going to use to sort of abbreviate this. So what's the deal here? Well, for this, for bulk degradation, basically any of these bonds within the material could degrade at any one point. If you remember, we had these, this chunk of material, all of it's bonded. As time goes on, it basically stays the same volume, but some of the bonds within it are breaking, and then at later times there's even less. Even fewer of those bonds left over. So basically the volume remains constant, water can diffuse freely through it and react with any of these bonds at any given time. So this is a process that's spatially uniform. So kind of within the whole system, I can sort of say, hey, this essentially applies to my whole system. So using this abbreviation here and using this idea here, I can basically say, hey, the D concentration of bonds dt is equal to minus K effective times the concentration of bonds. And what do we have here? Well, can we solve this equation here? Well, we might need to dust off the high school calculus a little bit, but this is a first order linear constant coefficient differential equation, ordinary differential equation. And we can dust off the high school calculus notes, or we could solve it. I could solve this via separation of variables. So we could bring the concentration of bonds over to this side. We could bring the dt over to the side. So we get d dB 1 over bonds is equal to minus K effective times T. Of course, we can integrate both sides. And let's integrate. So think a moment now. What might we want to put for integrations for bonds? Well, basically, we're trying to solve this differential equation, to basically try to get, this will give us concentration of bonds as a function of sort of any time later on. So I'm just going to integrate the right-hand side from 0 to just some arbitrary time later t. And we want to choose corresponding limits of integration for the left-hand side. So what is that going to be on the left-hand side? Well, at time 0, I'm going to have some initial concentration. I'll call it B naught, which is the concentration at some time t equals 0. And then I'm basically going to have some concentration of bonds at some later time that I care about here. And in this case, K effective is basically some known constant as well. So B naught's a known constant, K effective is a known constant. I can sub in whatever T I want. So you could use Wolfram alpha, you could, dust off your high school calculus notes, or you could stay tuned for the next minute, but basically what do we get here? If you integrate 1 over B, then you get natural log of B. And if you sub in these limits of integration, we basically get natural log of concentration of bonds minus natural log of B naught. And this is basically the initial bond concentration. And this is equal to, well, you're just integrating a constant, so we just get minus K effective times time. Of course, if you remember your natural log rules, when you subtract two natural logs, you can do natural log of them divided, and then we could take e to the both sides. And what do you get? Well, if you do out all of the algebra, you end up with the concentration of bonds is equal to the initial concentration of bonds times e to the minus k effective t. So what does this look like? This looks like exponential decay in bonds. So basically, we have some initial concentration of bonds, and if you subbed in t equals 0, e to the 0 would be 1. So initially we have b naught for bonds. As time goes to infinity, we get e to the minus infinity, so this approaches 0. So take a moment now and sketch what concentration of bonds looks like as a function of time. Well, at time equals 0, we have b naught right here, and then as time goes to infinity, we observe exponential decay in bonds. So this is b of t. So initially we have some bonds like this. So there we have it, right? This basically allows us to predict, and by knowing this k effective, that essentially gives us the idea of like how quickly we're going to be losing our bonds. Now, why do we care? Why do we care about being able to predict the number of bonds as a function of time? Well, the idea is a lot of times you might want to use these sorts of polymeric scaffolds for the delivery of drugs. So let's say I have drug tethered to a scaffold or a vehicle, a drug delivery vehicle, right? So let's say I have these drugs and I want to deliver them to a patient over time, right? And let's say this drug would be a drug that would be dangerous to give to the patient all at once, or maybe it's metabolized too quickly. So basically what do? I tie up this drug in some scaffold, and then I hope that as this scaffold degrades, that drug is released to the environment. So basically I take some drug and I covalently bind it to this scaffold. And then basically as the scaffold degrades, i.e. as our ester bonds break, some of those chunks of broken scaffold, these chunks of broken scaffold can come out, and some of the drug stays bound to the scaffold, but some of the scaffold leaves, and some of the scaffold leaves with the pieces of drug with it. And now this drug is essentially delivered to the patient. So this drug can basically go out with the degrading scaffold. So why do I care about being able to predict scaffold degradation? Well, if I can predict scaffold degradation, then I can predict rate of drug delivery. Why is that awesome? Well, let me tell you, if I can predict the rate of drug delivery, then I can make sure that this stays at a level that is below the toxic threshold to the patient, but above the minimum effective dose. So there's basically this therapeutic window that you want to keep. You want to keep the rate of drug delivery above what's therapeutic, but below what's dangerous to the patient. And these drug delivery vehicles for sort of extended release can enable that. And sometimes these drug scaffolds could be used for bulk degradation. Now, what's the tricky thing here? Well, the rate of delivery is basically proportional to minus d bonds d time. Why is it equal to minus this? Well, d bonds d time is something that's, this itself is negative. So putting the minus sign out here is basically the rate of delivery to the patient, right? Because basically this is the bonds remaining, right? So d bonds dt is something that's negative. All right, the slope of this graph right here is negative, and the rate of drug delivery to the patient is proportional to this, and in a sense it's proportional to like what fraction of those bonds are associated with a drug actually tethered to it compared to what fraction of these bonds are just normal structural bonds. So give or take, or I guess all in all, the rate of drug delivery to patient is proportional to minus d bonds dt. So take a moment now and sketch what minus dB dt looks like as a function of time. Well, we can always go back to this equation here, right? We already have this solution. So dB dt, right? We can take the derivative of this with respect to time. And what does that mean? Well, we basically get, you know, B naught's a constant out here, and you want to take the derivative of e to the something t. Well, you just bring this minus k effective down. Minus k effective down, and then you still keep the e to the whatever e to the minus k effective dt, or sorry, e to the minus k effective t. So if we want to plot minus dB dt, then we just put a minus sign out here, and we basically get b naught k effective times e to the minus dt. So this is still exponential decay. So basically this is still exponential decay. That looks like this. And basically this initial point here is b naught k effective. So basically the two factors that determine how quickly we deliver drug to the patient are basically how many bonds are there originally, or in a sense how much drug is loaded there initially, and what is the rate constant associated with the effective rate constant associated with this bond breaking process. So what does that mean? Well, we need to be careful with these bulk degrading devices. Why do we care? Well, we basically, you know, we want to make sure that at the beginning it's not too much. We want to make sure that it's not too much drug. And also, you know, this can potentially be problematic in the sense that, you know, even long after we'd, you know, ideally like to stop having given drug to the patient, it basically means that some drug could even be delivered after we wish to stop treatment. So some drug still delivered after desired stop. So that could be problematic, right? So what's the idea here? Well, you know, a lot of times we don't want to give all of our drug at the beginning, and we don't want that dose to taper off, right? You know, let's say I have a headache and I want to take some ibuprofen or something like that for my headache. Well, I don't want to start to get my headache symptoms back, you know, just a little bit of time into my dose, and I certainly don't want to give myself a toxic amount of that dose at the beginning, right? I basically want the drug delivery rate to be constant for a while, and then to basically suddenly stop right around the time it's time for me to take my next dose. I don't want these sort of tails to basically carry over long after I give it. So, you know, that's the deal with this bulk degradation, right? We essentially we can't escape this exponential decay. Or can we? Well, not via bulk degradation, but it turns out that via surface degradation, we might be able to have a different drug release profile. So surface degrading polymers they have a different release profile. And what do I mean by a different release profile? Well, let's see if we can predict this mathematically. And we'll spoiler alert, more calculus is coming, but we'll work through it together. And you know, hopefully,
we can basically have more constant during, so our goal is to have this be more constant during treatment, and then closer to 0 after completion, rather than this sort of exponential decay that's always delivering some of the drug to the patient. So let's talk about surface degrading polymers. So we're going to treat this a little bit. Different mathematically. And the idea with surface degrading polymers is the time rate of change. Right? Again, remember, volume is not constant. Not constant. And we're looking to essentially figure out the volume as a function of time. So what's the idea with surface degrading polymers is the degradation rate, the degradation rate is proportional to the amount of exposed surface area. So basically the idea is here, if I have some device and I have some surface area exposed, if you remember, the characteristic of surface degrading polymers is basically that water comes in and interacts with the polymer, and basically, anywhere on the surface is sort of eligible for that water to come in and react with, but that water can't really make it all the way to the bulk. So basically, water comes in, hits the surface, reacts, and then that surface erodes a little bit, and more surface is exposed underneath. So the idea here is whatever degradation rate we might observe is proportional to certainly some factors regarding the kinetics, regarding the chemistry, but it's also sort of related to this geometry of the amount of exposed surface area. So if we wanted to put this mathematically, I could say the time rate of change of the volume of my device, right? So there's some volume V. The time rate of change of that volume is essentially the degradation rate here, or related to the degradation rate. And I could basically say, hey, this is proportional to the amount of exposed surface area, right? So I could basically say, hey, this is proportional to the surface area, which I'll call SA. So I have some device that has some volume, it has some surface area. The time rate of change of volume is proportional to the surface area. But, this is a degradation process, so surface area is something positive, but its volume is decreasing with time. So dV dt is going to be negative when surface area is positive, so I'm going to need to put a minus sign out here. And of course, the units don't line up on either side, but if anytime you have something that's proportional to something else, you can put in some kind of proportionality constant, and I'll just put this proportionality constant, I'll just call this alpha. And this is a proportionality constant, and this proportionality constant is basically controlled by the chemistry of the material. So basically, so this material would certainly have, could have some K effective. That K effective would sort of get wrapped up. It is not exactly equal to, but it is related to and proportional to this this factor right here. So take a moment now, pause and ponder. What are the units of alpha? What are the units of this proportionality constant alpha in order to have both sides of the equation have the same units? Well, d volume dt, this has to have cubic meters per second, right? Volume is units of cubic meters. the time rate of change of that would be cubic meters per second. The surface area has to have units of meters squared. So if you look at the units of alpha, that's got to have units of meters per second. What else has units of meters per second? Well, you can kind of think of alpha as essentially like a velocity of the surface receding. Right, so basically, you know, we have some surface. You can almost imagine the surface, all of the sides of the surface is like rushing in towards the center. You can almost think of them rushing in towards the center with some speed. Now, of course, you know, we typically think of, you know, when you're doing like dynamics or something like that, a lot of times you would measure velocities in meters per second. You know, you might actually think of these as something like microns per month. If you were dealing with actual polymers, but it's still a unit of length divided by a unit of time. You know, it's just for polymers, this velocity is microns per month. You know, in contrast to meters per second, which we would use in, you know, for typical values in dynamics or something like that. But anyway, I digress. Here's the framework that we're going to be working with for things. Now, if you want to figure out what the volume of something is as a function of time, you know, you could certainly go ahead and do that. But if you're trying to basically set up and solve a differential equation, it might be nice to do so in terms of some variables that kind of characterize the volume and the surface area of something. And it turns out that a convenient way, you know, we're not going to get actually like a totally 100% precise answer for this. But the best way to approximate to get an approximate answer for the volume as a function of time is to approximate your drug delivery vehicle as one of three types of geometries. As one of three geometries. So what are the three geometries that we're going to do? We're going to look at a sphere. We're going to look at a rod, and we're going to look at a disk. So a sphere, I mean, don't need to draw a sphere for you right here, but you know, it's this, you know, right, there's a sphere. When I think about when I'm thinking about a rod, I'm thinking of something that basically has a length that is much larger than its radius. So it's basically it has a long length and a small radius. And for a disk, I'm thinking sort of it's still a cylinder, but sort of the opposite of the rod. So it has a large radius compared to its thickness. So if we want to think about these three geometries here and try to work towards characterizing the relationship between their surface area, their volume, and some form of this differential equation where we can work them out as a function of time. Well, let's work out what their surface areas and volumes are. So surface area and volume. And so if I wanted to characterize a sphere, I could do so with its radius r. And if you remember, if you dust off your high school geometry notes, the volume of a sphere is 4/3 pi r cubed. And if you wanted to characterize the surface area of a sphere, then it turns out to be 4 pi r squared. A rod we could characterize with a radius r and a length L. And the surface area of this rod sort of has two components. One component is sort of this face, the face right here, as well as the circular face at the end here. And then the other part of it is this sort of thing that would look like a rectangle if you kind of unwrapped it, right? So if you basically took a rod and kind of unwrapped it as a rectangle, one dimension of that rectangle would be the length L, and then the other would sort of be the circumference of that if you sort of imagined unwrapping that. So if we wanted to look at the surface area here, we essentially have two circles. So there's 2 pi r squareds. And then we also have this, this circumference times the length for the other component of that surface area. And so the circumference would be 2 pi r. And then the other length of that unwrapped rectangle would be L. So that's the surface area of the rod. If you want to think about the volume, it's basically the area of this circle times the length. So it would be pi r squared L would be that volume. And then the disk, well, the disk, let's call the disk as having some thickness h and having some radius r. And again, we can sort of formulate, the surface area. We have a top circular face and a bottom circular face, so we have 2 pi r squared, and then we also have this kind of edge of the coin almost, which would be 2 pi r h. Sorry, that's 2 pi r h. And then the volume would be pi r squared h. So this is basically what we can characterize here. And then for the rod, how will we approximate? How will we make some sort of approximation? So for the rod, well, we're basically going to say that L is much, much bigger than R while this is degrading. And for the disk, we're going to sort of say the opposite is true. R is much, much bigger than H. And we're going to sort of avoid things that are kind of pill-like this, where R and H are sort of a similar magnitude. Again, it's possible to mathematically characterize these, but it's not easy. And sphere, sphere doesn't really require any approximations at all, because its surface area and its volume are really just a function of radius. So what's the idea here? So what is our goal? Our goal is basically to derive the volume as a function of time. But for these 3 different geometries, we're going to have basically a different way of doing so. So for the sphere, our goal is basically to figure out what the radius is as a function of time. For the rod, our goal is to figure out what the radius is as a function of time, and we're basically going to assume that the length is approximately constant. And that's sort of related to this this idea here that, if its length, its radius changing is going to have a much greater effect on its volume change than its length changing, right? Its length is only slightly shortening as the degradation process goes along, but its radius, relative to its initial radius, is going to change. It's going to be changing a lot. And for a disk, our goal is to basically find the thickness as a function of time, because it's that that thickness is changing, and we're going to assume that its radius isn't really appreciably changing. Okay, strictly speaking, it is getting eroded a little bit away from the edge, but mostly, the biggest factor that's affecting its volume change is the erosion from the faces towards the center. So here's this disk. We're basically going to figure out volume as a function of time by figuring out the thickness as a function of time, and we're going to assume that that the radius, give or take a little bit, is constant. So again, these are approximations, and the bigger L is relative to R, or the bigger R is relative to H, the better these approximations kind of hold. So what can we do? We're going to take these surface area and volume expressions, and we're going to sub them into this differential equation for volume and surface area, and we're going to figure out, and we're going to use that to basically get a differential equation, and we're going to solve those differential equations for this. For the rest of the lecture, I'm just going to focus on how we do it for the disk, and I'm going to do the annoying professor thing where I say, and then I'll leave it as an exercise to the students to do the rod and the sphere. So let's do the disk. So, what am I going to do? I'm going to sub this expression for volume into the dv dt. So what does that look like? Basically, I have the time derivative of this expression for volume right here, pi r squared h. And this is going to be equal to minus alpha times the surface area, which I have right here, which is just, for the disk, 2 pi r squared plus 2 pi r h. So there we have it. All right. Now, well, what can we do? Strictly speaking, r and h are time varying. So when I take the derivative of two things that could both be functions of time, I need to use the product rule for taking derivatives. So if you remember the product rule, it's like first times derivative of second, so it's pi r squared times dh dt, plus second, I mean pi is a constant that's along for the ride, so it's times second h times the derivative of first, which would be d r squared dt. And then of course I have this right hand side is just coming along for the ride. So I have my minus alpha 2 pi r squared plus 2 pi rh. All right. And this thing right here, I need to use the chain rule for. So this is going to be equal to 2 r dr dt. If you remember, like, this derivative is with respect to time, right? It's like the two comes down in r, and then I have to chain rule that r squared, because I'm not taking the derivative of r squared with respect to r, I'm taking the derivative of r squared with respect to t. So when I chain rule all of that out, this is what I have here. So finally, I have pi r squared dh dt plus pi h r, I guess 2 pi h r dr dt, and now I have this minus alpha 2 pi r squared, and I'm gonna distribute the minus alpha, and I have a minus alpha 2 pi rh. Now you might be like, oh geez, Lannon, it's filling up a page with calculus. What's going on here? We got derivatives of two separate things, right? You promised that we'd be able to just solve for h as a function of time, and where's this r equals constant kind of going in here, right? How can we have this if r is a constant? Well, let's do a trick. And again, as a student, I always hated these tricks when the professor was like, okay, and then there's a trick that makes the answer really obvious. Yeah, so, well, it's my pleasure to do that now. Sorry. So, here's the trick. Let's divide by pi r squared. I'm allowed to do that. The math police aren't going to come get me. So what am I left once I divide by pi r squared? I have dh dt plus, and if I divide by pi r squared, then here I have 2h over pi r. Nope, sorry, the pi's cancel out. I have 2h over r dr dt. Did I do that right? I have a pi r squared. Yep. And then here I have minus alpha just minus 2 alpha, right? Yep, minus 2 alpha. Right, because I still have that 2, but the pi r squared cancels out. And then here I have minus 2 alpha h over r. This is still a somewhat messy differential equation, but what can we do? Well, we can notice some terms are larger than others. So, pause and ponder. If I were to keep just 2 of the 4 terms, which ones? Which ones would I keep? Which ones would you keep? Which ones? Which ones would you keep? Well, if you remember, hopefully you've had a chance to pause and ponder. If you remember, for the disk, r is much, much bigger than h. So that means h over r is super small. So this and this, these are super small compared to, well, compared to 1, right? If h is much, much less than r, then basically these terms don't really have much of an effect in the overall equation. It's these terms that end up dominating. So what does this mean? This basically means dh dt is approximately equal to minus 2 alpha. Physically, what does this mean? Well, if you remember, alpha was that velocity with which the surface is receding, and basically h is shrinking at a rate of 2 alpha because it's shrinking at a rate of 1 alpha from one side and 1 alpha from another side. So, geez, do we even really need to go through all of this calculus? I mean, you could have just told me dh dt is minus 2 alpha, and I'd be like, yeah, okay, that makes sense, right? It's 1 alpha from one side and 1 alpha from the other. But we did something a little bit more mathematically rigorous to get there. So what does that mean? Well, we can basically say if we wanted to separate variables and integrate, we could integrate dh, we could integrate minus 2 alpha dt, and if we wanted to set appropriate limits of integration, again, we want to integrate t from 0 to t just to sort of have this as a function of time. What h corresponds to 0? Well, we might say, hey, there's some known original thickness, some initial thickness, so some thickness at time equals 0, and then this is going to become some h of t at some later time. You integrate the left-hand side, and you get h of t minus h naught is equal to, you integrate the left-hand side, and you get minus 2 alpha t, or if you want to just solve it for h of t, you get you bring the h naught over to the side, and you get h naught minus 2 alpha t. And if you wanted to sort of bring back this idea here, when you're going to re-estimate the volume of this disk, we could say, well, give or take a little bit, R is constant. And if it's constant, then you could basically say that it's basically equal to some initial radius R naught. So if we wanted our volume as a function of time of the disk, what's that going to look like? Well, that's going to look like pi r squared h. And if we use that approximation, if we use this approximation, r being the initial radius and h being this h of t that we just derived, then we could say that this is approximately equal to pi r naught squared, and then this expression for h that we just had. So h naught minus 2 alpha t. So what's the key thing with this volume of the disk? We'll take a moment now and plot what the volume looks like as a function of time. Well, hopefully you've had a chance to pause and ponder. If you sub it in at t equals 0, then it just starts off at pi r naught squared h naught. And if you look at this is basically the equation of a line, right? It's the equation of a line with some negative slope. So it goes on, and then until we get to this point right here, at which the volume is practically 0. And this is basically at t is equal to h naught over 2 alpha. Right? If you can basically sub it in, at what time does the volume approach 0? This time right here. And what's cool about this? Well, we basically have a constant slope. And if you picture this idea of a disk, of a thin disk, with a bunch of drug embedded throughout, if the time rate of change of volume basically means that drug gets released anytime that corresponding amount of volume got degraded into it, basically if the drug elution rate, so if the drug delivery rate is proportional to minus dV dt, then what does that mean? This basically means the drug delivery rate, well, what does that look like? That basically means the drug delivery rate is like negative the slope of this curve right here. So it basically means the drug delivery rate is constant, and then it just ends right here. So this is great. This is awesome, right? This is exactly what we want. We want a constant drug delivery rate until it runs out, and then when it runs out, we don't want to give drugs to the patient anymore, and we're done. So these flat disks are almost the ideal drug delivery devices, where they give a constant amount and then they're done, and after they're done, they've stopped. Or almost stopped. What's the key thing here is mathematically this predicts, this is what the math says, but of course negative volume doesn't really make any sense. What happens in real life is we sort of get some decay right here. So what might cause real life to deviate from the math? So why? So take a moment now. What might cause, once this volume gets really, really low right here, what's causing, what sort of new physics take over, or what fundamental assumptions have taken over to sort of make it such that we don't get silly things like negative volume, that we get some sort of more gradual taper off? right? Some magical, or some more gradual taper off in the drug delivery rate after this point right here. Well, the key thing here is physically, when we're at this point right here, the disk is very thin. And, well, what happens when the disk is very thin? If you remember, the second Domkohler number is K effective over the diffusivity divided by some length scale squared. And in particular, for this, the appropriate length scale would essentially be h over 2 for a disk, right? The length scale is from the surface to sort of the center of the device, and that shortest distance is basically the half thickness of that disk, right? So this would be like the diffusivity, the second Domkohler number is K effective over the diffusivity of h over 2. And basically, what does this mean? Well, surface erosion is only true when this is big. So surface erosion only when big. And basically what happens? Well, once the disk gets really thin, then instead of surface erosion being really big, the second Domkohler number is small, because basically this is equal to K times, this should be squared, h over 2 squared over the diffusivity. And basically once h gets really small, the second Domkohler number gets small. And basically, like, once the disk gets very thin, it transitions to bulk erosion. But hopefully by the time this has transitioned to bulk erosion, there's not actually that much of the drug left. So even though in real life it tapers off like this, who cares? So what's the key thing here? Well, we can actually, if we want to tune disks to deliver drugs to people at appropriate rates, we have a lot of parameters that we can play around with. We can play around with the concentration of drug within the disk. We can play around with the thickness. And the thicker you make the drug, the longer you make it last, the longer you make this drug delivery vehicle last. Also the more area you give the drug, the faster you can elute drug delivery to the patient. So you can play around with the thickness, you can play around with the radius, you can play around with the chemistry of the ester bonds and how quickly those break. You can play around with the concentration of drug within these things. There's a huge design space to explore in these drug delivery vehicles, and it's not just it's not just the chemistry, it's the geometry as well. So hopefully I've given you some cool things to think about in terms of mathematical models to predict polymer degradation. Thanks for watching, and good luck with your study of biomaterials.